Welcome to Module 2 of Radio System Design on Analog Modulation Basics. Today we're going to talk about the basic idea of AM, FM, and PM modulation. That's amplitude, frequency, and phase. We're just going to go over a very high simplistic level just to make sure we're all on the same page before we get into talking about specific wireless systems. Alright, so why do we need to modulate signals? Well, it turns out, why do we need to modulate them, and also why do we need radio waves? That's probably a question you've never asked yourself, but there's an important reason why we use radio. And it's because electromagnetic waves propagate where sound and light do not. Now you may stop for a second and say, hey, wait a second, light is an electromagnetic wave. And it is. And you can think about waves from 0 hertz up to hundreds of terahertz as all being electromagnetic waves. Wireless systems generally are operating around a few kilohertz all the way up to nowadays even a couple hundred gigahertz. And the reason why we use electromagnetic waves in these frequencies is that they propagate far. And they penetrate a lot of materials. For example, low frequency waves like AM radio might have wavelengths on the order of hundreds of meters, and therefore really small structures like a house or a wall is pretty transparent to something with such a long wavelength, whereas light has a very short wavelength, and it may reflect off of very thin objects, metals. So for a good example is the metal in your house would never affect an AM radio wave. However, if you shined a light on a metal nail in the wall, it would reflect off. And that's just because of the wavelength properties of the two. So longer wavelengths can help out, but we don't always transmit at really low frequencies or long wavelengths. We oftentimes go into much higher frequencies. Cell phones operate around 900 megahertz, Wi-Fi is at 2.4 and at 5 gigahertz, and WiMAX now is coming out at 60 gigahertz. And the reason why we choose different frequencies is that really for two reasons. One is the attenuation of different frequencies is different. So for instance, one of the reasons why people choose 60 gigahertz is because it actually is absorbed by the atmosphere. And you're thinking, well, why would I choose a frequency that gets absorbed? And it's actually because if you're putting a bunch of wireless routers in a building, you don't want them all to conflict with one another and talk over one another. So if their range is naturally short, it allows you to make a nice local network. Another reason why we choose different frequencies is we'll learn later the data we can transmit is related to the bandwidth, and typically we don't modulate signals with any more than 10% of the bandwidth of our carrier signal. So 60 gigahertz, the fastest bandwidth signal we would have would be roughly 6 gigahertz. So this is sort of the motivation for using electromagnetic waves for transmitting information as opposed to sound or light. One thing I'd like to point out is that a single tone, so cosine omega t, carries power, but it doesn't carry information. We'll learn a little bit later on, but there's sort of an abstract notion of information as being represented in the change of something. So if I were to come in and turn on a sinusoid and turn it off and turn it on, this would be like Morse code, for instance. The information is contained in the changes. Just like if I wrote a word that was all M's for all time, there's no way that could contain any information because the letters don't change. However, if I were to write the word mom, it's the change in the letters that carries some information for us. And this is a bit abstract, but basically what I want you to think about is the fact that a carrier itself can't contain any information. And we'll learn a little bit later on there is an exception to that, but we need a separate reference, and that has to do with single sideband. But enough about that. What we're looking at, though, therefore, is to transmit information is we need to have a carrier that changes, and therefore we need modulation. And that's how we convey information onto an electromagnetic wave so that we can transmit it through the air. All right, so the information is a signal that's generally much lower in frequency than our carrier. As I said before, typically it's less than 0.1 times FC. And that just has to do with the fact that it's challenging to build circuits and systems that can actually use a wider bandwidth than 10%. The radio frequency signal is generally a single carrier, cosine or sine. Just a quick notice, the difference between cosine omega t and sine omega t. If we're just looking at a single signal, we can't tell the difference. We only know the difference between them when we have both present, and we just notice a phase difference. So the carrier, sine, cosine, doesn't matter what you call it. It's only when you have another version that has a 90 degrees phase shift do you need to start paying attention to which one you call cosine and sine, just so you can have them. In wireless systems, we generally refer to these simply as the in phase and the quadrature signal, and we just forget the whole idea of cosine and sine. And the basic idea of modulation is just shown right down here. We're just going to take this low frequency signal and we are going to apply it onto a carrier. The carrier will allow transmission of the signal through the air at that specific frequency, so we get all the properties of the carrier's ability to travel for whatever reason, and along with it, it's taking the information that we wish to convey. So modulation refers to turning information into electrical signals which are suitable for transmission. And just a quick thing on terminology. An electrical signal is modulated by data, but not the other way around. Sometimes students tend to say the data is modulated on the signal. It's actually the signal that gets modulated by the data, but that's just a nuance. So let's talk about modulation types. So the signal properties are varied according to the information. So what do we mean by that? Let's look at some of the properties of an RF signal. I've listed here in blue 3 different properties: the amplitude, the frequency, and the phase. And these are 3 different knobs, if you will, that we can vary to convey information. This variation could be continuous as in analog modulation, or in discrete steps as in digital modulation. And just a quick look ahead, it turns out that we don't transmit perfect sharp edges, so even digital modulation ends up being analog. And for all those analog engineers out there, you know that the digital world eventually has to become analog to get into the real world. So us analog designers still have an important job. All right, so the way we modulate a signal really depends upon a bunch of constraints. And generally we make the decision based upon things like complexity, bandwidth, sensitivity to noise, sensitivity to nonlinearity. One great example that I use is AM versus FM radio. And I got to be frank, I don't even listen to the radio anymore, but back in the day there was AM and FM radio. And AM is the simplest radio, but oftentimes the quality wasn't as good as we would like. And initially people said AM was the best choice because it uses the smallest bandwidth, and FM was a bad idea because it uses more bandwidth than an AM signal. But after a while, people learned, in particular, Shannon showed us that we can actually increase the signal-to-noise ratio by increasing the bandwidth that we use. And so the way to think about it is in frequency modulation, if we take a signal and use a very large frequency modulation, we can actually increase the signal-to-noise. So here's a great example where we would decide to do frequency modulation instead of amplitude modulation because it'll allow us to use a wider bandwidth, and as we'll learn later, that actually translates into a better signal-to-noise ratio. And that's why your FM radio sounds better, is because it can use a wider bandwidth than AM, and because of that it can get better sound quality. So let's talk about basic AM modulation. And the idea is we've got some signal in the time domain and we're going to multiply it by a carrier, and it's pretty intuitive just to see this is the waveform that you get out. So from the time domain, this is pretty intuitive, but as we talked about in the previous module, going from the time to the frequency involves a little bit of understanding the Fourier transform and what happens when we do this multiplication in the time domain. I should point out that in RF systems, we're often looking at symbols like this, and you need to know whether you're looking at a time or a frequency as a signal coming in. Let me just make this as an F here. And what do I mean by that? I mean oftentimes you'll have a box and you'll have an arrow and you'll have this and you'll have another box and an arrow, and this is multiplication in the time domain. And you just have to remember that. Even though you could be looking at the spectrum of that and the spectrum of that, we're always talking about multiplication in the time domain by this. It's called a mixer, but you may have already known that. So let's look at what happens in the frequency domain. So if you remember from last time we talked about the carrier, well, here's the Fourier transform of a cosine of omega t. And so the question is, what does the frequency domain of this signal look like? And multiplication in the time domain corresponds to convolution in the frequency domain. And you'll notice here this is not a mistake. This is not multiplication or the dot. We sometimes have multiplication. It is a convolution with this little asterisk here. So because we're multiplying in the time domain, we need to convolve in the frequency domain. And what that's going to do qualitatively is it's going to take this baseband signal, which is the spectrum of this envelope here, right? And it's going to place it on top of the two carriers. I'm just going to take a minute to review convolution because I think it's just an important thing that you remember where it comes from and also how to do it. Most of what we're going to do in wireless systems is this simple: take the baseband and pluck it on top of two delta functions. But let's just go over it real quick. So here is the convolution of two signals in the frequency domain, and you'll notice I'm back to omega. Remember, we can go from omega to F, it doesn't matter. And what you're doing is, let's just take an example of two signals, and I'm going to draw a box here. This is omega, this is x of omega, and then I'll draw here triangle. This is y of omega. Okay. So what we're going to do is we have this dummy variable that we're integrating over. And so if you recall, what we do is we actually take the two signals and we're going to multiply them. So I'm going to multiply this signal by the top signal, and it is shifted by an amount, eta. And what I'm going to do is I'm going to sweep eta as eta moves, and so this will slowly move along. And I'm just going to do an example right here. What this integral does is it actually calculates the area overlap, the product of these two, calculates the area, and then it plots for that value of eta. We'll call this eta naught. For eta naught, it plots a single point which represents the multiplication of those two integrated over the entire area. And then we'll end up with a convolution that will look something like this. So that's just a reminder. And if in RF, all of our signals are generally symmetric, just for the sake of completeness. If y of omega had looked like this, you'll notice that omega's here and eta's shifted. And so what we do is we actually would take this and flip it. And so it would be x of omega, and this we would walk in this way. and that flip happens because of what's inside of these parentheses. So this is just kind of reminding you of the integral. What I want to do is do a short video where I show you two examples so you can see qualitatively how we do this. So I wanted to show an example of convolution just to give you a refresher. On the left I have a signal with two triangular spectra, if you will, and on the right I have what might be familiar as a baseband, but basically another triangle centered at 0. And we're going to imagine that in the time domain we're going to multiply these two signals. So in the frequency domain we are going to convolve them. And as we discussed before, to do the convolution we basically take the one waveform, we flip it in the x-axis because this is a triangle to be symmetric, and then we basically start at negative infinity and we just slowly walk that signal in, and we look at the area that overlaps between this signal and this blue signal as it marches along with delta F in this example. And what we're going to plot is the magnitude of the area. We're not plotting the multiplication of the two. We basically calculate the overlapping area, and that is what we plot. So we're plotting an area, not an absolute value. And I chose two triangles because it'll give you a good example of how the convolution is of the area, not just a multiplication. So you can see the red triangle coming in from the left, and the overlapping area is being plotted at the top. And you can see that we get a nice smooth curve, and this is because of the way that the two areas overlap, because at each delta F we're integrating from minus infinity to the current frequency. So basically we're integrating the overlap between the two curves. So this is a great example of two triangles. Just to kind of give you a reminder, I now want to do a special example where we're going to do two delta functions, and that'll be more like what we would see for the standard multiplication of a carrier wave or convolution of cosine with a signal. And here we go. You can see on the left with the blue I have two delta functions, and they're not exactly a delta function. I made them thin triangles, thin squares to represent a delta function, but we're doing the same convolution, and what you can see is because they're very thin, you basically get a perfect reproduction, almost perfect reproduction of your original spectra, and it is centered at 3 and 3, which is exactly where the two delta functions are. So this is just a quick reminder of the convolution. When we multiply the signal on the left by the signal on the right in the time domain, we convolve them in the frequency domain. And a simple way of thinking about it when they're just delta functions is you're going to take this spectrum here in the red and you just plunk it down wherever there's a delta function. You can look at this again and see how the convolution is actually done, but as long as you remember I just take this and put it down where each delta function is, you'll have a good idea. All right, now that we've gone over convolution, we can go back to our amplitude modulation, if you will. And what we have here is just an example of, let's say our spectrum was a little bit more complicated, and if we multiply it by cosine, all we do is we just take this just like before, and the center at 0 is going to go right here, and it's actually going to go also right here on the negative. But if we just look at the positive, here's the center. So this was the center that's right there, and we've got what we call an upper sideband and a lower sideband, and this is all positive frequency. So if you're wondering why am I showing this, it's because this piece that for the original signal was the negative side, the e to the minus j omega t. This was the image, if you will, of our signal here that's required for it to be real. When we do the multiplication, that actually gets up converted into the positive frequency space. So now we have these two signals, and if I were to plot this complete spectrum, just erase these real quick, and I were to extend this, we would have here in the negative. So we end up with 4 copies, where here we only had 2. And that's because each one of these gets a copy of what's there. So this is just a brief definition of a lower sideband and upper sideband, and it has to do with this center frequency when we do up conversions. I want to talk finally just about what happens when there's a DC component at our baseband frequency. And this is something that actually happens a lot in radios. And if we multiply that in the time domain by our cosine, we take all of this and we're going to drop it right on top of each one of these delta functions. And what we're going to end up with is this. It's going to end up right there. And we end up with the carrier. So not only are we transmitting the signal, both the upper and the lower sidebands of the signal, we're also transmitting the carrier. And the reason why we care about this is the carrier, as I mentioned before, doesn't carry, forgive me, information. And therefore, we're wasting power by transmitting it. And so you might say, well, let's just not do this. And that's a great idea, but it turns out that oftentimes, even though we don't like it, there are reasons why there's a little bit of a DC signal, and so we end up with a little bit of a carrier here. It becomes a little bit of a problem. And this is actually the basics of AM types of modulation. And so there's a couple different things of AM modulation that we'll talk about in the next module. You can do double sideband suppressed carrier, single sideband. These are all different architectures. And I'll just go back here. Actually, I'll just show you right here, just as a... All right, so here's some variations that we can do for AM. Some variations of the architectures are double sideband suppressed carrier, single sideband, and I just want to touch on something quickly here. Go back to this slide, and I showed you that we're going to have 4 copies of this, right? How many copies do we need to recreate the original signal? We only need 2, right? So I could have this one and get my signal just fine. I don't need these extra pieces. And so one of the things we'll learn about in AM is that we can transmit both sidebands, or we can just transmit one of those sidebands to save energy. And we'll talk more about that in the next module. And like I said before, the reason to choose different AM architectures is based upon power, bandwidth, system complexity, and perhaps other design trade-offs. So now we want to talk about phase and frequency modulation. And just want to point out, in the most general form, we can write an RF signal as cosine of phi of t. And phi of t is called the total phase. And it can have a time-varying frequency, and it can have a time-varying phase. And initially, this is a little bit of a hard concept, because normally we think about phase as cosine of omega t plus phi, and we think about, that's our phase. But in reality, all of this is our phase. Because remember, a cosine is just looking for some number to put in here, right? It doesn't care what it is. And so this is the argument of cosine. It's just that conveniently over time we've split these up into a time varying one, into one based on omega and one based on phi. One depends upon time and one doesn't, but both could depend upon time. And if this is your phase, then what's frequency? I thought this omega was frequency. Well, we generally define the instantaneous frequency as d phi dt. And I'll just do a quick example so you feel comfortable with that. Cosine of 2 pi ft plus pi over 2. If I asked you what the frequency of that was, you'd say, it's f, right? Well, according to this, we take phi and we take the time rate of change of that. So d dt of 2 pi f t plus pi over 2 equals f, right? Actually equals 2 pi, right? And so you can see right away that this is consistent with everything you've known before. It's just easier to talk about this phi of t, and the reason we do is that when we talk about modulation, we're really talking about just modulating phi of t, whether we do it by changing the frequency or changing a static phase, if you will, is just a matter of semantics, because mathematically we're just looking at changing phi of t. And so phase modulation we can think about as a fixed frequency, we modulate the phase, or frequency modulation can just be written as the time integral of our phase change, or we could actually have omega c change. But this changing with time is equivalent to having omega c change with time, because it's all about phi of t. All right, so that's a little bit of mathematics about phase and frequency modulation, and here's just an example of an FM-PM waveform. Sometimes it's really hard to tell whether it's frequency or phase modulated, and the reason is because there is no difference, right? We're just changing that argument of cosine and sine. A couple comments. Typically in phase and frequency modulation, the amplitude is constant, which makes the signal immune to noise, which is good. The data is usually contained in the zero crossing intervals, and one bad part is that typically phase and frequency modulation, because remember it's cosine of phi of t, right? Or we're modulating phi of t. Well, this is a nonlinear function, therefore our bandwidth tends to be very large. All right. Okay, this was just a quick summary of the basic ideas of AM, FM, and phase modulation, and we also covered a little bit on a convolution just as a quick refresher for you.